Okay, welcome back. What I want to look at today is something called data handling and probability, experimental probability. Okay, and that's what I want to look at today. Now, please note that this is work that I have delivered previously before. Okay, so I believe that these were sanctioned and they've been paid for. Okay. Now, here we have contents, relative frequency, tallying, probability, and investigation. Okay. Let me just go up a little bit so we can get it in. Okay. Now, relative frequency. Experimental probability is equal to the relative frequency when the experiment has been done many times. The formula for calculating relative frequency and hence experimental probability is shown below. Relative frequency equals number of results of an event over number of trials of that event. Okay. Okay. Let's pan back, make sure we get everything in. Now the objective to know formula for relative frequency. Okay. Now tallying. Tallying. Okay. Remember, single one equals 1. 2 of these equals 2. 4 stripes equals 4. And 4 stripes and a bar across equals 5. Okay. Just go back, make sure we got everything in for you. Okay, in frame. Okay. Now here, the objective is to know how to tally. So let's look at that. State the numerical equivalence of each of these tallies. So we have tallies, we have 5, 5, 10, and 1 is 13. 5 add 4 equals, and I'm waiting for you to tell me, 9. 5 add 5 plus 4 equals, and I'm still waiting for you to tell me, 14. 5 add 2 equals, now tell me about it, 7. 3 stripes equals 3, of course. And here we have 5, 10, 15, 20. And you're going to tell me the answer here is 22. Okay. Okay, right. Now keep in mind, once, as we said here, once you reach a 5, you put a 4 and or 5. Once you reach a 5, you put a bar. That makes 5. So it's common practice. It doesn't matter whether you're in China, Russia, Egypt, the UK, France, or any part of the world. This tally system still applies. Okay, it is universal. Okay. Now see here, as I said, 13, 9, and the next one's going to be what? 14. Okay. 7, 3, and what did we say it was, the last one? Now tell me, I'm waiting for you, okay? Thank you, 22. Now we are going to use these tallies to bring about some data. And we're going to look at using our data in a manner that gives us a result based on the unexpected. Okay. Example of relative frequency. Okay, so let's look at relative frequency. Let me just move in a bit, make sure we can get this in view. Okay. Example of relative frequency. Okay. Just pan back, pan back, pan back, pan back. Okay. Now here are the results of rolling a dice 10 times. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 times. So we roll the dice first and we got a 3. Roll the dice second time, we got 6. Third time 6. Fourth time 1. Fifth time 2. 6 times 4. 7 is a 6. 8 is a 1. 9 is a 4. 10 is a 2. Okay, so we need to put these tallies or results into a table. And that is our table. Let me just pull back, start tying back, so make sure we got it all in frame. Okay, that's our table. Number of dice, number on dice 1 only appeared twice. Okay, so you can see that 1 had appeared twice, 2 had appeared twice, 3 had appeared once, 4 had appeared twice, 5 not at all, 6 had appeared 3 times. Okay. So we have given a frequency here 2, 2, 1, 2, 0, 3. Now, what is the relative frequency of each number on the dice? Now, remember that relative frequency equals number of results of an event over number of trials. So, here we have frequency 2, okay, etc. So the frequency of 1 is 2 times. Frequency of 2 is also 2 times. Okay. Make sure we're in frame. Okay, right here. Okay. Right, let me just go back a little bit so you can see where this is coming from. Okay. Now, what is the relative frequency of each number on the dice? We know the number on the dice is 1, and that appears twice. Okay. Okay, so number on dice is 1, relative frequency 1 over 5. Now here, what we're looking at is 2 results divided by 10 trials, because we have 10 trials. Okay, sorry about that. Let me just get it back in the frame. Okay, so and again we have 2 results, 10 trials. Now 1 result divided by 10 trials, 2 results divided by 10 trials, no results divided by 10 trials, 3 results divided by 10 trials. So Sorry, I'm off half frame. Just wait to get into focus. So sorry, I was just trying to work out something there, and it's quite correct. Okay, yep. That's it. So here we have the number on the dice: 1, 2, 3, 4, 5, 6, and we know that we're looking for the relative frequency now. Okay. Let me just make sure I get this into frame. Okay, let me just see if I can make this any clearer or simpler. Okay, let me just make sure that I've got this. Okay, number of results of an event. And we have 10 trials. Okay. So this would be correct. Okay, the results 2 divided by 10. Okay. Just make sure that I've cut everything in frame. Okay, just bear with me for a second. Thank you. Okay. And resting shot. Good. Okay, thank you. Just trying to make sure that I got this down right and that result is there. Okay, yep. So all this is trying to tell you here is that that is equal to 3/10, that is equal to 1/5. Okay. What they've done here is to reduce this down to, sorry about that. Okay, that becomes 1/5, that becomes 1/10. Again here 1/5 and 1/5. Okay, just simply just divide top and bottom by 2. Okay. Now, relative frequency. Copy the table on the next slide are the results of an experiment where an American penny was tossed 50 times. How many heads and how many tails would you expect? What is the probability of getting a head or tail based on the experiment? Table showing 50 coin tosses. Okay. Coin, heads or tails, tally. Okay, frequency. Let's have a look at that. Now that's the relative frequency of results. Heads, tails, etc., etc. Okay. Now frequency, relative frequency answers. How many heads and how many tails would you expect? What is the probability of getting a head or tail based on the experiment? Now we have a table here of the table showing 50 coin tosses. Heads we have 5, 10, 15, 20, 25, 27. Tails we have 5, 10, 15, 20, 23. Okay? Just make sure we got it in frame. Okay? Good. Now, relative frequency answer. Using the above formula in theory, we would expect the probability. Using the above formula in theory, we would expect the probability of getting a head or tail to be 1 in 2. Because you've only got 2 choices, heads or tails. Okay? But relative frequency equals number of results of an event over number of trials. Using the relative frequency formula, our experimental results have achieved head equal 27 over 50 and tail equal 23 over 50. So you can see it's not quite 50-50, is it? As you can see, the relative frequency is close to the theoretical results. Okay. And again, number of results of an event. Okay, so the event again is number of heads, number of trials. We had 50 trials. Okay. Events 27, trials 50, and the trial you'll notice is constant in both cases. Okay, so keep that in mind. Probability on a coin has a probability of 1/2. A 6 on a dice has probability of 1/6. So in reference to our probabilities, we can therefore assume that theoretical probability equals number of successes over number of possible outcomes. A head on a coin has a probability of 1/2, 1 over 2. A 6 on a dice has a probability of 1 in 6. Relative frequency equals number of results of an event over number of trials. Okay. In an experiment Peter conducted that a head has a probability of 1/3. In another experiment, Peter concluded that the probability of a 6 on a dice was 1 in 9. Can you explain why? Well, I'm going to leave you with that to figure out for yourself. Again, don't forget, always do some additional research. Look back at your maths work especially. There's some good books in school, use them, okay? Now, relative frequency is based on an experiment. An experimental result gets closer and closer to the theoretical result when the number of trials are increased. If Bart did 100 trials and Lisa did 100,000, then Lisa's relative frequency should be closer to the theoretical probability. Okay, so what it is trying to say here is that the more trials you do, the more likelihood you are likely to get to a theoretical aspect and nearer a precise value than if you did fewer trials. That reminds me a bit like the experimentals that's going on at the moment in trying to find a vaccine for COVID-19. The amount of trials that they've got to do, and that will take time. Investigation. Investigate whether increasing the number of the trials of rolling a dice would give probabilities closer to 1/6 for each number. Instruction. Experiment in pains, make a hypothesis and then test it. Decide how to record your results, think about, and then produce a joint write-up. Okay? Now here, main findings. If you combine the results of the whole class in a table, you'll find that increasing the number of trials does make the probability get closer to the theoretical probability. If you did a considerable number of trials, for example thousands or millions, you will get even closer to the theoretical probability. Okay. Relative frequency results, okay, probability, number of trials. So you can see that here at approximately 500 trials we get into a point where heads and tails actually becomes equal to each other. But that's only after a number of trials, showing you that you get closer to the actual theoretical probability than otherwise. So you can almost say at this point here, they're both equal, so 50-50. I would just for simplicity. As you can see, the more trials are undertaken, the closer the lines get to 0.5. Okay. The probability tends towards the theoretical 0.5 value. Okay. Or 0.5, 50-50. Okay, thank you. I hope you found this useful. Have a good day. Bye-bye.